Today we're going to learn about radioactivity, the 3 different types of nuclear decay, and then how to write chemical equations for nuclear decay. So first, let's just start off by defining what radioactivity is. Radioactivity is just when energy is released from an unstable nuclei. So some elements have nuclei that are unstable, which means they're naturally going to break down until they reach a stable nuclei. And during this process of breaking down, energy is released. And so that energy is what we refer to as radioactivity. There's 3 different types of radioactive decay. The first one is called alpha decay. In alpha decay, the original nucleus is going to break down into a different nucleus, and in the process, it's going to release something called an alpha particle. The second type is called beta decay, where it's very similar. So the nucleus breaks down and in the process releases a beta particle. And the third type is called gamma decay. During gamma decay, the nucleus doesn't change, but it does emit high amounts of energy. And then before I get into the types of decay, I just want to review how we write atomic symbols. So if you need to, go ahead and copy this down in your notes. Because when we talk about alpha particles and beta particles, even gamma, we follow this format. Okay. So the symbol is going to go in the middle. Okay. Either we'll use like alpha, beta, but we'll also use element symbols. Okay. And then the top left number, this is going to be the mass number. So always the number of protons plus neutrons. And then the bottom left number is the atomic number or the number of protons. Our first type of decay is called alpha decay. So during alpha decay, a nucleus, it decays into a smaller nucleus, and in the process, it loses something called an alpha particle. Okay. So that alpha particle, it just has 2 protons and 2 neutrons to it. Okay. So then on your notes, you need to write what an alpha particle looks like. So if it has 2 protons and 2 neutrons, what's its mass number? 4. 2 plus 2. Okay, so for the mass number, we're going to write 4. The bottom left number is the number of protons. So how many protons does it have? 2. Okay. And then we're going to write this symbol for alpha. It's like kind of like a goofy lowercase a, or does it kind of look like a fat Jesus fish? Okay, so that's how we would write an alpha particle. Or there's another common way to write it. The mass number is still 4. Protons is still 2. And then if you look at the periodic table, what element has 2 protons and a mass of 4? Okay, helium. You'll also frequently see it written as this. Okay, either of these options are fine. Today you'll see me use both interchangeably just so you can see them either way, but you can pick if you like the alpha or the helium better. One thing I want to point out, an alpha particle is just a helium nucleus, okay? It's not a whole helium atom. It doesn't have like the electrons around it, okay? So just the nucleus of a helium. Okay. This type of radiation, it's the least penetrating, so it means that like if you were to hold up a piece of paper, alpha radiation, like it can't go through paper, okay? If it were to like come at you, it can't go through your skin, okay? So a real world application is like smoke detectors, okay? So like how many of you have smoke detectors in your house? All of you, right? So your smoke detectors, they emit these little alpha particles, but again, these are not on like the list of concerning particles, right? Like holding a piece of paper stops it. Your skin blocks it, because so can like alpha particles make it to like your internal organs. No. Okay, next we have beta decay. So during beta decay, a neutron is going to decay into a proton. When that happens, it emits this little beta particle. So we're going to write down the beta particle. A beta particle doesn't have a mass. Okay, so 0 is your top number. It's essentially an electron. So instead of like a 1, we're going to do a -1 because it has a -1 charge. And then the symbol for beta, it's like a B with a little tail at the bottom. Or you can write 0, -1, and it's essentially an electron, so you could do an E for an electron. Okay. And again, either of these are used to represent beta particles. I say it's like 50-50. Okay, so you can use either or. Today, I'll use them like interchangeably just so you can see it both ways. Okay. These types of particles, they're a little bit more penetrating than alpha. So if you like held up like beta radiation in front of paper, like it can go through paper. But if you were to hold up aluminum foil, like aluminum foil would stop it. Okay. Some real life applications, they're used in like medical tracers and then like carbon dating. So trying to figure out how old things are. And then the last one is gamma radiation. Okay. During gamma decay, the nucleus doesn't change. It just gives off high energy. Electromagnetic radiation, so that's like light energy. But it's not in the visible light spectrum. It's higher energy, so think like X-rays and gamma rays. So this one, no mass, no charge. And then gamma, it kind of looks like a capital Y with like a loop at the base. And that's your only option for gamma. Okay, so that's what a gamma particle looks like. These ones are the most penetrating, probably the most damaging. Like if you're going to be concerned about radiation, this is the one you should be concerned about. So this time, like if you were to hold up paper to gamma radiation, it's going to go straight through. If you were to hold up your aluminum foil, it would go straight through. You'd have to block it with like some thick lead or concrete. Okay. Applications, medical imaging, so think like X-rays, MRIs. Okay. And how many of you, like you go to the dentist, do you get your X-rays taken once a year at the dentist? Okay. What does the dentist lay over you when they take your X-rays? Like that apron thing, right? And is it light or heavy? Heavy. Why do you think it's heavy? What's on the inside? What kind of protection? Which one of these do you think is on the inside? The lead, right? So the whole point of that is they don't want any like radiation to like scatter and like, you don't need radiation hitting the rest of your cells. Like we just want to capture your teeth, right? So reducing risks of any damage. Okay.